So, good evening, all. We'll start today's session. We'll first revise what we have done in week 9, and then we'll follow it up with our tutorial session for the assignment number 9. Okay, so in week 9, we have discussed about the Peltier device. So, Peltier device is basically just a second. Okay, yeah. So yes, so Peltier device is basically a device that is used to either convert temperature difference into electrical energy or electrical energy into some kind of temperature difference. So it is basically a semiconductor material junction. It is made up of P and N type semiconductor junctions, and then it is used as a heat pump. So we all have seen water pump in our houses, right? Whenever we need to put the water from the underground tank to our top tank, we specifically have to use some kind of pump because natural flow of water is from top top tank to bottom tank. Because if water is in top tank, we won't need external pump in order to get the water flow. But if you want to put water from the underground tank to the top tank, we have to use some kind of water pump. Similarly, there is heat pump. So we all know that naturally energy will flow from higher temperature to lower temperature. We know that that is what naturally happens. But when we want to do the energy flow from low temperature to higher temperature, then we'll need something like an external pump, that is heat pump. And Peltier device is one way of achieving that. So why specifically are we talking about Peltier devices? Because they like solar PV is a new hot topic. Similarly, Peltier devices are also have come up recently. Initially, their efficiency was very less, but they have come into picture and they are getting better and better day by day. So as I mentioned, Peltier is used for heat pump when it transfers heat from cold body to hot body, that is from lower temperature to higher temperature. How does it work? By providing an electrical energy input at its terminals. It is used in a lot of applications like refrigeration, cooling, generating heat, etc. We look at some of the applications when we go ahead. So what is the basic principle of this device? So if you consider two dissimilar metals, suppose nickel and copper, when you connect these two metals, then there will be a junction point. So what happens is, when you make a current flow, when you apply some voltage and you make current flow through these terminals, then you will observe that the at the junction points, at one junction it is a hot junction, another junction becomes a cold junction. Depending on in which direction the current is flowing, uh, it becomes hot or cold depending on the direction of current. But it always have this temperature difference. So this effect is called Peltier effect. And the word Peltier came from the name of the scientist who discovered this. And again, the direction of current is very important. So if current is flowing from copper to nickel, then it will become hot. If current is flowing from nickel to copper, then it will become cold. So depend if we change the direction of current, then our hot and cold junctions will be reversed accordingly. Okay, so you have to take care of this factor into mind. Now, heat absorbed or generated, this heat at these junctions, here at cold junction, heat will be absorbed. At the hot junction, heat will be given. So this heat absorbed or generated is proportional to the current that you flow through this module. And this equation is given as Q is equals to pi I, where pi is called the Peltier coefficient. This is proportional to the current that you flow through the Peltier module. If you look at the basic structure of the Peltier module, it is a series of lot of P and N junctions, and the current flow direction is something like this. If you apply a battery like this, then current flows like this, N, P, N, P. These are connected like this here. Copper substrates are present, and then to insulate this from the external environment, ceramic or any other kind of insulators are used. Okay, so this is you have seen in the lectures also. This is a Peltier module. It sort of looks like our mobile phone batteries. Like initially, removable batteries used to come now in our mobile phones. It is similar. It looks like that, very very thin, and because of the ceramic, it's very cold to touch. So these are the two terminals through which we give the voltage to the Peltier module, and one side of this will be hot, and another side of this will be cold. So this is the like practical Peltier module, small size, the smallest size available. Now, depending on your application, when you want to design a big system, then you connect these modules in series and parallel. Okay, so in order to design a bigger system, you do that. Okay, so again, the Peltier module. So what happens is, as we have seen, that it's a series of N and P junctions, and then one of the surface becomes cold, another becomes hot, and these purple kind of joints are present inside the module, which are made up of copper, because copper has very high conductivity. Therefore, we use copper strips to connect at the bottom inside the module, and then there is ceramic substrate at the top in order to insulate this module from the ambient. Now, as we mentioned, that Peltier works as a heat pump. So if I have one cold junction which is at temperature T1, I have another, and if I have another hot junction which is at temperature T2, and I want to pump more energy from the cold junction and give it to the hot junction, this won't happen naturally, right? Because naturally tendency of heat is to flow from higher temperature to lower temperature, right? From hot to cold. But if we want to flow the energy from cold to hot, we need to put some external work in it, right? This is the basic principle. So here we put the work in the form of electrical energy. We give electrical energy as input in order to pump QC amount of heat from the cold junction and give it to the hot junction. So this is the basic principle diagram of Peltier module when it is used as a heat pump. And now when Peltier module is used as a heat pump, in order to measure the performance of this Peltier module, we have a term or a parameter called coefficient of performance. This coefficient of performance is the ratio of this QC heat that we are removing from the cold junction to the electrical energy that we had to put in order to remove this heat. So QC by E tells us the performance. So ideally we want the least amount of electrical energy. We want to pump the maximum amount of energy from the cold junction by giving least amount of electrical input. That means we want least value of QE for maximum value of QC. That means ideally we desire coefficient of performance to be very high value. And QC here is normally we denote for the joules, but here we are denoting QC as energy extracted from the cold junction. And when we are talking about energy extraction, it's the flow of heat, right? And whenever we talk about flow, that means with respect to time. That means rate of energy. And this rate of energy is d by dt of joules. And d by dt of joules is, as we know, it's power and its units will be in watts or joules per second. Therefore, it's not normally joules, it's watts here because we are talking about heat flow. Now, as we had already seen, whenever we talk about a new element and we are using it, before doing that, we try to understand the data sheet of that parameter. So the Peltier element data sheet, there are few, important parameters. The performance specifications are the most important parameters. So depending on what hot side temperature are you desiring, you have different variations. So depending on whether your hot side temperature is 25 degrees Celsius or 50 degrees Celsius, you will use the separate columns. Now, then there is another parameter called Qmax. Qmax is the maximum amount of heat that Peltier module can be used to remove from the cold junction. So, if you are putting a Peltier module, then that is the maximum energy or heat flow that the Peltier module can do. Then delta max is the maximum delta temperature that Peltier module can sustain across it. Imax is the maximum current that can flow through the Peltier module. Vmax is the maximum voltage that can be applied to the Peltier module terminals. And module resistance. So, as we have mentioned, equivalently, any device can be seen as an equivalent impedance. So, when you look at from this side, look at these terminals, then there is a resistance of this Peltier module that is RP. This RP is given by this module resistance parameter. So this, when you have this diagram and you try to make an equivalent of this like this, then this RP is the resistance. Then this RP is the resistance that is given in the data sheet. Now, we would say why is this QC max rating given here? So what happens is, ideally we will think that the more the current will flow through the Peltier module, the more amount of QC it should be able to pump out. It should not have any limit ideally. But practically what happens, as you know that there is this series resistance RP, what happens is when you increase QC beyond the limit, the I square R losses across this RP increases to a very high extent. And because of that, the power flow will reduce instead of increasing. We would think that QC should increase if we are increasing the voltage, but if beyond a certain limit, QC will start to decrease again because of this RP and the I square R losses happening inside it. And because the QC will decrease again, the delta, that is the temperature difference between T1 and T2, will again start reducing, which is what we don't want. We want to keep the temperature difference to as high as possible. Like in solar module, we wanted to operate the solar module always at maximum power point. Similarly, here we want to operate our Peltier module to maintain maximum delta T. Okay. And another specification is maximum operating temperature rating. So in datasheet of all the modules, like for this particular module, that datasheet that sir has used, 80 degrees Celsius is the maximum temperature that this module can operate. Now, now there are performance curves for the module. So performance curves, there are two types of performance curves, thermal and electric. So the thermal curves gives QC versus delta T, and the electric curve gives the voltage versus delta T. So now you will see that there are various different current. For various values of this current, there are various curves. So each curve is corresponding to different value of current IP. Now you will see that as you will see, as the delta T value decreases, the QC that can be pumped from the module increases. So that means as we reduce the delta T, the QC that we can pump increases. So this is what we can conclude from the thermal curve. Now from the electric curve, more the QC, higher must also be the power you have to pump. Now the more amount of heat you want to pump, the more amount of electrical power you have to give. That means electrical power is the product of voltage and current. That means higher the voltage and current that you will have to give. So power pumped into the Peltier module, as you can see in this diagram, it's Vp into Ip. It's product of the voltage that you're applying across the Peltier terminals and the current that is flowing through it. So if you just look at a schematic diagram, then we know that this voltage, we suppose we want to interface the Peltier module with solar PV, which is abundantly available. So we just take the solar module. We know that we can put a DC to DC converter here, and this duty cycle we can vary depending on at what operating point we want to operate. And the voltage output voltage of this DC to DC converter will act as Vp, that is the voltage that will be applied to the Peltier terminals, and IP will be the current that will decide the operating point based on these characteristics. Okay. So now here one problem that occurs is, as we have been talking from the start of the class, that energy has a natural tendency to flow from hot hot junction to cold junction, right? Whenever something is hot, when we take a hot plate of food, then our food starts to cool by itself, right? That is what naturally happens. So in order to make this, and here what we are trying to do is the opposite of what naturally happens. We are trying to pull out the energy from the cold junction and give it to the hot junction. So this is what we are trying to do externally. But while we are trying to do this, naturally energy will flow from the hot junction to cold junction from the sides. So if I don't isolate this hot part, or I don't dissipate this hot part's energy into the atmosphere, then what will happen is my system won't work properly, because this hot junction will be giving its energy, to the cold junction like this. And what I'm trying to do is I'm trying to pull out energy in this direction, and it is naturally trying to flow in this direction. So effectively, if I don't insulate this junction properly, or I don't dissipate its heat somewhere else, then this, suppose I am taking 10 watts of energy, 10 watts of heat from this direction, and 10 watts I'm giving in is coming in this direction, then equivalently I am getting no work done, right? It is of no use. So therefore I have to insulate this. the hot junction, or I have to make sure that the energy that is present in this hot junction is dissipated to the external atmosphere so that it does not come back to the cold junction. If I cannot ensure that, my system won't work effectively. Now, in order to understand thermal domain, which is not exactly our domain, right? We are sort of inclined towards electrical, and so in order to make equivalency of the thermal domain to electrical domain, we try to analyze these thermal systems using a sort of an electrical equivalent model. Now, how we are doing that is, suppose I have this green PCB and I have a red component mounted on the PCB, and this is some kind of integrated circuit, some IC is there that I am placing on the PCB. Now, I know that when my IC will be operating at its junction, some amount of heat will be generated, and my purpose is to dissipate this heat to the ambient. So now, in order to convert this to thermal equivalent model, what we do is we consider nodes. So one is our node, that is the junction, that is our one node. Another is the ambient, that is we are considering the component, and the component is directly in contact with the air in its surroundings, right? So we can consider two nodes. One we can call J junction node, another will be the ambient node. Now we know that QC is the amount of heat that we want to pump out from the junction to the ambient. So we can name this as QC. The source we can name it as QC, or the power. Okay, that will be in watts. And there will be always a certain kind of resistance, thermal resistance, that will be in the form of an insulating air. So the resistance, that is thermal resistance, it can be emulated in electrical circuit as an electrical resistance, that can be called as R theta JA, because that is a thermal resistance between junction node J and junction node A. That is why it's called R theta JA. Now, as you can see an equivalent representation of this circuit as this, where this is a voltage source, current I is flowing, and this is a resistance, where this I is equivalent to QC, voltage is equivalent to Tj minus Ta, that is the temperature difference across the junction, and R is equivalent to R theta Ja. So this is the equivalency that we were trying to, because we already know the series circuit, yeah, right? We always deal with a simple electrical circuit. So it's very easy for us to understand when we model any kind of thermal component in terms of this kind of model. So based on the equivalency that we already know, we can write the equation from this thermal equivalent circuit as voltage difference across points Tj minus Ta is equals to V is equals to I into R. So V is Tj minus Ta, I is the QC, and R is the thermal resistance. So this is the equivalent, it's equivalent to the electrical KVL, Kirchhoff's voltage law, right? And from this we can obtain a formula to obtain the junction temperature. Now, if in this particular example, if I try to consider an ambient temperature of 40 degrees Celsius, and thermal resistance of 10 degrees Celsius per watt, and QC of 20 watts, then you can see that the junction temperature comes out to be around 240 degrees Celsius. This 240 degrees Celsius is very high. Any IC that you take, and if you look at the data sheet of these ICs, you will see that the junction temperature does not go beyond 180 degrees Celsius. Max to max, it will go around 200 degrees Celsius. Normally, it's from 150 degrees Celsius to 180 degrees Celsius. Okay. So now this is 240. This is very high. So we need to put some external mechanism here in order to reduce this temperature. Now, in this equation, if you will see, in this equation, QC is not in our control. QC depends on what kind of IC you are using, whether it's a what kind of IC it is, depending on the from one IC to another, amount of QC that we need to pump out varies. So QC is not in our control. Ambient temperature is also not in our control, and the junction temperature is the one we are finding. So the only parameter that is in our control is the thermal resistance. So how can we reduce the junction temperature? In order to reduce the junction temperature, we can try controlling R theta Ja. That is the thermal resistance of our system. Now, how can we control R theta JA? In order to control the thermal resistance, let us first see the component breakdown of this thermal resistance. So if you break the circuit into initially there were just two nodes, the J node and the A node. Now there are three nodes. We are breaking the resistance into three parts. This is junction. This is the case of the IC. C represents the case of the IC, and A is the ambient again. So if I break my R theta JA, this was initially R theta JA. If I break my R theta JA into R theta JC and R theta CA, then what I'll observe is I theta JC is very small. It's around of the the value is around zero point 0.5 degrees Celsius per watt, and R theta C is 9.5 degrees Celsius per watt, which is very high. So it's clear from this breakdown that this is the parameter that we would want to focus our energy on, right? We would try to reduce this parameter, and once we reduce this parameter, our junction from the equation that we just saw, this equation number one, our junction temperature will automatically come down. Okay, so now our aim is to reduce R theta Ca, that is thermal resistance between the case to ambient. That means we need to put something above the IC so that it dissipates heat to the ambient at a much more better rate. So the first thing that comes to our mind is a heat sink. So let us put a heat sink here. This is our component, the red component, and above that we'll just put a heat sink and see what happens. Okay, so when we are putting this heat sink here, then we have introduced another node. So initially they were just J, C and A. Now there are J, C, S for heatsink and A. Now if you again make the thermal equivalent model of this thermal system, then you will observe that between the junction to case there will be one thermal resistance, between case to sink there will be another thermal resistance, and between sink to ambient there will be another thermal resistance. So most of you might have used heat sinks, right? So you all know that you put a thermal paste between this IC and heat sink here. The reason of putting the thermal paste is to reduce R theta CS, this parameter. And the value of R theta CS depends on what kind of thermal paste you are using. Okay. So if based on the previous calculations you will observe the breakdown, then you will see that R theta JC is of the magnitude of 0.5 degrees Celsius for watt. R theta CS is also reduced, but still R theta SA. That means the thermal resistance between sink and the ambient is still very high. Between these two, still we can work something out. These two parameters are already reduced to a low value. So we'll see how can we reduce this parameter. In order to further improve this, we could put a Peltier, or we could put a fan here. So there are a lot of ways to do it. So let us try to use Peltier here. Now what Peltier will do here? Peltier will the green junction of Peltier, that is the cold junction, we will put on the side of the component, and the hot junction we will put on the side of the heat sink, so that Peltier will pump the heat from this hot component into the heat sink. It is doing some external work. Initially, we had just put the heat sink, so it was happening naturally. Now here we are forcing the heat from the hot component to the heat sink. Okay, and we know that in order to drive Peltier, we need a DC to DC converter, and we can give the energy to DC to DC converter using a solar module or any other DC source. Now, when you are designing this system, then for Peltier, you need three parameters: QC, IP, and delta T. Now, QC value depends on what component is present here. If I am trying to cool a microprocessor, then QC will be very high. If I am trying to cool a very simple basic IC, then QC will be comparatively less. And we know from the datasheet of Peltier that this QC should be less than Qmax of the Peltier module that we select. So this QC will come from the IC that we are using. This IP will depend on the value of QC. From the performance characteristics, we can obtain this value of IP, and we'll need to make sure that this IP is less than the Imax rating that is given in the datasheet of the Peltier module. Also, we know that there is a parameter called delta T, maximum delta T rating, and given in the datasheet, our delta T desired should be less than the delta T maximum rating that is given in the datasheet, And also this thing, delta T, what we want comes from this system. What is the temperature of this side and what is the temperature we are desiring for the heat sink? That will determine our delta T. Okay, so based on our application, we will decide QC and delta T values, and then based on these values, we will try to pick up a Peltier module whose these ratings are not exceeded. Okay, this delta T should be less than delta T max. This will also come from the data sheet, right? Now, if we just take an example where the delta T that we desire is 15 degrees Celsius and the heat that we are planning to get removed is 20 watts. Then let us see how we can use the performance curves. So this is a QC versus delta T curve. Now I know that I want delta T to be around 15 degrees Celsius. So I'll just stretch a line from here, right? Then it will give me these blue points: 1, 2, 3, 4, and 5 points. So these are the 5 operating points. I need to pick from that. Now, I also know that I want QC of 20 watts. So this QC of 20 watts, if I try to draw a horizontal line from that, there is only one operating point that comes around that area. So we'll just, and that this performance curve is corresponding to IP or the Peltier current equal to 3 amperes. That means if we want to maintain 15 degrees Celsius delta T, and if you want to remove the heat, if you want to remove 20 watts of heat, then we'll have to use the Peltier module with 3 amps power supply. Okay, we have to give 3 amperes current to it. So this is how we use the performance characteristics. Again, the point that we have been talking about is we need to make sure that the heat from the sink is removed to the ambient. Otherwise, all this heat will come to the component again. This kind of flow will be happening here. We need to pump this heat outside to the ambient. Otherwise, this heat might come back to the component like this, and this will reduce the efficiency of our system because our Peltier has a limitation of operating at a delta T maximum. So, if the heat sink is not dissipating to the ambient properly, then its temperature will increase. And if its temperature increases, then temperature of the cold junction will also increase, which will reduce the efficiency of our Peltier system. Okay, so that is why we won't want it. So we would design a system in such a way that all the heat that is generated, that is given to the heat sink, is again effectively pumped to the ambient or the environment near it, so that it does not come back to this module. We don't want this. Okay. Again, if we want to increase the efficiency of the system further, we could also add a fan to the system. Okay. Now this fan can be given power supply from the same DC to DC converter. This could be a multi-output DC to DC converter that we could use here, and this whole system will is called as thermoelectric controller. Okay. Now, if we try to understand what is happening in the thermal domain, then the heat flow that is happening is affected by four mechanisms: conduction, convection, radiation, and mass transport. So we'll try to look at these modes of or the mechanisms of heat flow in a bit detail, because we want to calculate because if until we calculate, we cannot decide what size of heat sink we need, whether we need the fan or not, whether we need the Peltier module or not. All these things depend on the absolute values that we will calculate. And in order to calculate, we need to first understand what is happening when I'm talking about conduction. When is conduction happening? When is convection happening? We need to have a very minimal understanding of these things. Okay. Now, the basic thermal relationship that comes across is Q is equals to delta T by R theta. This is called the Fourier relationship. And there are different terminologies in which you can find this relation. If there is an aluminum block or some kind of conducting block, and Q is the amount of heat that is flowing in this direction. On one side temperature is T1, another side temperature is T2, and this heat flow is happening in this direction, and perpendicular to it we have this area. That area is the or perpendicular area to the direction of heat flow. Then Q is equals to delta T by R theta, where where you can convert this expression into multiple kinds of expression that are already available. So if you know this orthogonal area, or area orthogonal to the heat flow direction, then you can just, if you just divide Q by A, then it is called a specific power. Then in order to convert this expression into specific power, we will divide the whole expression by capital A, and then you can obtain Q is equals to delta T by small r theta. This small r is called thermal resistivity. Capital R theta is thermal resistance, small r theta is thermal resistivity, and the H is thermal coefficient. So this is again the like summarizing all the three forms in this equation, in which this equation can be written. Okay. Now when we talk about heat transfer by conduction, conduction is between two solids. Okay, so if we talk about the conduction in this particular solid block, which through across which we are trying to flow heat amount of Q, and the thickness across which we are trying to flow is delta X, and on one side of this block temperature is T1, another side temperature is T2. Then where if you use the thermal coefficient form, then Q will be equal to H times delta theta. This is the thermal equivalent form that we had just seen before, where where there is a constant K, which is given as H times delta X, and H is K by delta X. So using this in this equation, you can obtain Q is equals to Ka delta T by delta X, where this equation is called heat flow rate equation or Fourier law. So this is the equation. So the only thing that you need to understand from this part is what when does conduction happen, and this is the equation that we need to use for when we are talking about conduction. Q is equals to Ka into delta T by delta X. And what is the significance of these parameters? What is K, what is A, what is delta X? Okay, all these things you have to remember just. And from this equation, we know that Q is equals to delta T by R theta. We already know that. So from that, we can say that thermal resistance is equals to delta X by Ka. So when we are designing any kind of thermal system, based on this relation, we can say that when we increase the this orthogonal area, then thermal resistance will reduce, and vice versa. So all these parameters can be controlled in order to effectively obtain the thermal resistance value. Okay. Now this is the same expression again, and these K values are given for different materials. So these are the thermal conductivity values. So if you'll observe, then it's 410, 385 for different materials. Silver has the highest K value, and still still air and thermocol has almost the lowest K values, thermal conductivity values. So depending on what kind of material you are choosing, this is how material selection happens. So if sometimes you don't have to change the heatsink, you can just change the material that the heatsink is made of with the same dimensions. So all these, each and everything plays an important role when we are designing any kind of system. Now, we had talked about heat transfer by conduction so far. Now, heat transfer by convection. So, convection happens between a solid and a fluid. And there are two types of convection: free convection and forced convection. Now, in order to understand convection, let's consider that there is a hot body. There is a hot plate that is lying on the floor. Now, what happens is there is air in the contact of this body, right? The air very closest, that is marked in the dark orange here, will be at a very high temperature because of the diffusion that is happening here. From the hot body, the diffusion is happening, and this will make the vicinity, air in the vicinity, very hot. Comparatively, at some top column, that is the blue column, you will observe that the air is at a very low temperature. Now, because the orange column is at high temperature and the blue column is at low temperature, what happens is since the hot air has very less density, so it is very light, so it will try to move upwards, and this hot air is moving upwards, and similarly this cold air, which is heavier, will come down. So sort of these currents, air currents are formed here. So all these currents lead to the natural flow of air and it helps to cool this hot body, because when the moment this hot air here is replaced by cold again, then higher diffusion will happen, then again this will become hot, and this process will keep on going again and again until the hot body becomes equal to the ambient temperature. That is the condition when equilibrium will be attained. So this is what is called a free convection, because here we are not putting any external thing, we had just kept the hot body in air, and this is happening naturally, therefore it's called free convection. Now when you talk about convection, we cannot still use the same formula. So for convection, based on the basic thermal relationship, we try to modify the formula by adding a parameter called characteristic dimension. This parameter x, if you multiply and divide it by x, then capital X by delta X is a number called Nusselt's number. So when you talk about convection, you have to first calculate Nusselt's number n, which is given by this formula Q is equals to Ka n delta T by X. And similarly, thermal resistances can be obtained in terms of Nusselt's number from this expression. And so whenever you have to calculate this for heat transfer by convection, you have to calculate the Nusselt number. Now, how do you calculate Nusselt number? So, the Nusselt number Nusselt number has few of the empirical relations that have been found out from experiments, and it depends on what kind of convection is going on, whether the convection is a free convection or forced convection. Depending on the type of convection, we calculate Nusselt number. Now, when we talk about free convection, we have to first calculate a Rayleigh number using this formula, and then from Rayleigh number we can obtain the Nusselt number. Similarly, for forced convection, we have to first calculate the Reynolds number, and then we can calculate the Nusselt number from the Reynolds number. And these are very standard formulas, and all of these things you already know. And you just need to understand. You just need to know the right formula to be used, and what are the significance of these things. What does X signify? What does delta, the thermal diffusivity of fluid? Nu is the kinematic viscosity. All these parameters, if you understand the meaning, you can go ahead with the right formula. Okay. Now, when we talk if you talk about free convection for standard solids, then if you can consider a horizontal flat plate, then the characteristic dimension is given by a plus b by 2, where a and b are the two sides of this rectangle. Similarly, for a circulate horizontal plate, D is the characteristic dimension. And similarly, depending on laminar flow and turbulent flow. So laminar flow is the if you imagine a tap like this. Suppose this is a tap in my washroom, and if the water from my tap is flowing like this, it is called laminar flow. And this, if I have another tap in the washroom and water from my tap is flowing at a very fast rate, so this we can call it as turbulent flow. So these are just terminal. So in order to classify this flow as laminar and this as turbulent, we have certain numbers. So this is what the Rayleigh number tells us. So depending on the Rayleigh number and the Reynolds number, we try to classify our system as laminar or turbulent, and depending on these flow, we calculate the Nusselt number using the respective equations. So again we have the expression for vertical flat plate. So the main thing you need to remember here is the characteristic dimension x. So when the flow is happening vertically, b is the you need to see the direction in which it is happening, and then you take the parameter along that direction. So here again, if vertical we are considering, then it will be along the diameter. Similarly, for horizontal cylindrical solid, heat flow will be in heat flow will be like this. Therefore, D is a characteristic. Similarly, for vertical, heat flow will be like this. So it will be along the length L. So you just need to, depending on the shape of of the of the device that we are considering convective flow, depending on the shape of that device, whether we are having a cylindrical heat sink or a rectangular heat sink, depending on that surface and the direction in which heat flow is happening, we we find the value of this characteristic dimension, and based on that we can find the Nusselt number. Similarly, we have the expression for parallel flat plates, and then we have forced convection. So when I put a fan externally to this, then we call it forced convection. Again, here again, standard formulas are present. You just have to find the value of x. Now, in order to understand this properly, Zara has discussed a very nice example. So, if I have this container, green container, that is a conductive surface, and I want to refrigerate it. So, what could be the application here? If you can think, you recently have heard everybody has got COVID vaccines, right? And when you talk about a vaccine cannot be kept at just any random temperature. A vaccine need to be maintained within a certain temperature range. So normally when people come to put you vaccines, they have their small containers with them. They are small refrigerators. So usually this application is used in medical domain where you might need very small containers and you might need to use them as refrigerators. So their Peltier module is used. So if you put this inside a thermocol for proper insulation, and this purple thing is our Peltier module, and I put an aluminum block on the top of the Peltier module in order to dissipate the heat of Peltier module's hot junction to air. Okay. Now from this aluminum block that I have put here to the external atmosphere, sorry, this is a cylindrical block. So from this cylindrical block at the top of the Peltier module, heat is going into the atmosphere. That means here at the surface of this block, solid is interacting with the fluid in the vicinity. Yes, Shrikant, please go ahead with your question. Okay, if anyone has any doubts, you can stop me in between and you can ask. Okay, just unmute yourself and ask. Okay, so yeah, so here if we have at the boundary of this cylindrical block, if I have this cylindrical block, then here this heat, if this is very hot, then it will dissipate heat to the ambient, right? Then at the boundary of this, solid is interacting with fluid. That means convection is happening, right? So and here since or fan is not present, we can call it free convection. Now if you look at this cylinder again, then what is happening is the block is something like this, right? And here my Peltier module is kept. Now heat will be dissipating from the sides and from the top. So these are the only two places from where heat will be dissipating, right? So from the top, it will, if you look at a cylindrical block from the top, it will look like a circular flat plate, right? If I look at the top, my block will be like this, right? And from the sides, it will be like a hollow cylinder. So depending on these shapes, the circular plate and the hollow cylinder, we will find the area A, and based on that, we will calculate our relay number and the Nusselt's number. So for circular flat plate, we know that the relay number is given by this formula, and we know all these standard values from the respective science table, and depending on what material we are using. So currently we are considering air as the fluid, and this V and delta are correspondingly for air. Now based on these, we'll find if we calculate the value of A, it comes out to be this, and from that we can calculate the Nusselt number based on the range of A, and we'll obtain the expression, and then from that we can calculate the Nusselt number. And we know that if we once have the Nusselt number, we already know the value of K for air. We know the value of A, that is the orthogonal area of cross section, which will be a circle again for cylindrical, that is pi by 4 d square. And when we put these values in the expression, we'll be able to obtain the heat dissipation from the top side. Now, when we look at the sides, as we discussed, it will be a cylinder, right? For cylinder, the curved surface area will be 2 pi r into h, or we can call it pi dh, or 2 pi r into h. So depending on this area, again, we can calculate this value of k, and it will come out to be some value. So this will give us the total heat that is given to the ambient. Now, from this diagram, we know that QC is the amount of heat that this Peltier module is pumping. E is the electrical input, and QH is this heat that is dissipated by the aluminum block into the atmosphere. So we know that QC plus E will gives us QH. That means QC is equals to QH minus E. So when you substitute the same here instead of QC QH minus E, then you obtain the expression. And when you substitute these values, you obtain the coefficient of performance. And using the coefficient of performance, you can obtain the value of QC. Now you see that the heat required here was 14.4 watts. That means the heat that we could pump from the from for the refrigeration was only 14.4 watts when we just use the aluminum block. Now, if I add fan to it and do the similar calculations, now the moment I am adding fan here, I am moving into forced convection. So my formula will change. Initially, it was free convection. So if I calculate the values again, then I will obtain that QC comes out to be 56 watts. Initially, QC was only 14.4 watts, and then it came to be 50, came out to be 56 watt just by adding a fan. So you see the impact of adding on. So depending on your application, if you want to pump more amount of QC, then you have to try to design a system accordingly. Next comes heat transfer by radiation. So radiation is a transfer mechanism from a hot body through electromagnetic waves. Electromagnetic waves does not need any medium for transferring. So the formula for heat transfer by radiation is Q is equals to HR into A into delta T, where A is the area of the surface perpendicular to radiation direction and HR is the radiation thermal coefficient. And the value of HR can be found out using this formula. So whenever there is a hot body, it always will have a tendency to radiate. And if we assume that there is some reference that is a temperature T2, then based on these values you can obtain the heat that this hot body is radiating. And the last mode of heat transfer mechanism is heat transfer by mass transport. So movement of a fluid mass is used for transporting heat from one place to another. That is called mass transport. So, in your refrigerators, behind you have seen a snake-like structure, right? All of us have seen this kind of structure. Pipes are there and they go like this, like this. So, what happens there is, so there a lot of heat is generated inside the refrigerator. So, we put a coolant inside these pipes. Coolant is coolant is a kind of liquid that has higher tendency to absorb heat. So it will absorb the heat when this, so our part that we need to cool will be placed in contact with this pipe. So suppose this is my surface that is getting heated. I will put these pipes on the top of this, and then when the coolant is flowing in contact with this hot block, then it will take the heat from the hot block and it will go out, and then it will have another area where it will go, and then it will dissipate this heat in the air. And when it comes back through this path, then again it is cool now. And then it will, so if you the part that you see in the refrigerator, so suppose this is my hot block, okay, so my and this is my pipe, okay. Now here coolant is coming in, okay, and here coolant is going out, and then it is again coming back like this. It's a closed circuit, okay. So now what is happening here is, so when my coolant is cool, when it is coming in here, while it is in contact with the hot body, it is taking heat from the hot body. Now my coolant is circulated in pipes in contact with air. So while this flow is happening, the heat energy that I had taken from this hot block is given to the air, and during this path my coolant has again become cool, and then again I will circulate the coolant here, then again it will take the heat, then it will dissipate the heat to air again, and then again it will come and take the heat. So it will be operating in a closed form. So this is what is happening in our refrigerators, okay. So this is an example of mass transport, heat transfer by mass transport, okay. So another example is engines, our car engines. If you open the bonnet, then you will see that this kind of pipes are present there also. So there also this kind of mass transport flow, mass transport, heat transfer by mass transport is being used. So To understand mass transport, let us take this example. And here our aim is to cool this block, red block. We need to take the heat energy from this red block. Okay, and to do that I am using my purple Peltier module, and this pipe that is present here, I will be circulating a fluid inside this pipe. That pipe will take the heat from the Peltier module, and then it will go, and then it will keep on again. Cold fluid will come, it will take the heat, then again it will go. So again this will keep on happening again and again. Okay, so for the heat transfer using mass transport, the equation that is used is dm by d theta, dm by dt into Cp into delta T. So Cp is the specific heat of the fluid, and dm by dt is the mass flow rate. So depending on these parameters, at what rate I am flowing this fluid at what speed I am flowing with respect to time, and what is the specific heat of the fluid, what kind of fluid it is, whether it's a freon or it's normal water, what kind of fluid we are using. All these parameters will determine the heat that we are able to pump from this junction. Okay, so these are all the standard formulas for different types of heat transfer mechanisms. Now based on that, we look at the assignments. Any doubts so far? Okay, so we'll move on to the assignment calculation. So this was assignment number 9. It was a pretty simple and straightforward assignment. So if you look at problem number 1, specifications of a thermoelectric Peltier module from a datasheet is shown here. A 20-volt battery is connected to the thermoelectric Peltier module via a series resistance Rs as shown in the figure below. What is the theoretical value of the resistance Rs such that it will satisfy all the parameters or ratings for the given specifications? Now, we know that in the circuit where this is the Peltier module, this is our resistance Rs, this is our 20-volt battery. We know that this is the current IP that is flowing, and this is our Vp voltage. We know that using KVL, we can write this equation. Then we can write that Rs depends on Vp and Ip. And from the data sheet, we can see that Imax and Vmax parameters are given for two different hot side temperatures, 25 and 50 degrees Celsius, both they are given. So, since it's not clearly mentioned, let us calculate for both the scenarios and see what happens. Uh, suppose this is for hot side temperature 25 degrees Celsius, this is for hot side temperature 50 degrees Celsius. Okay, so here Rs will be equal to 20 minus Vp max for 25 is 14.4 by 6.4, and here it's 20 minus 16.4 by 6.4. So this comes out to be 0.875 ohms, and this comes out to be 0.5625 ohms. So we'll take the maximum value of the two, because we know we need to make sure that we don't cross any of these maximum ratings, right? So we'll take the maximum, that is, we'll take this value of Rs. Now, let us move on to the next problem. Following the given specifications, what is the minimum temperature of cold side when hot side temperature is 25 degrees Celsius? Since they have clearly given hot side temperatures, we just look at this column. Now they have asked minimum temperature for the cold side. Now we know that delta T maximum for hot side 25 degrees Celsius is given as 66 degrees Celsius, right? So delta T is equals to T hot minus T cold, right? So T cold will be equal to TH minus delta T. TH is given as 25 degrees Celsius, delta T maximum is 66 degrees Celsius. So TC minimum will be given as, add one more step, TH minus delta T maximum. So this is given as 25 degrees Celsius minus 66 degrees Celsius. And this TC minimum comes out to be minus 41 degrees. So in problem 3, for the specifications of a Peltier cooler shown below, what is the maximum coefficient of performance when hot side Peltier cooler is having a temperature of 27 degrees Celsius and operating at maximum current and voltage? Now we know that coefficient of performance is given by QC by E, and in order to find maximum value of this, we need to find the maximum value of QC also. And the operating point is given as maximum current and voltage. So at this operating point, electrical energy will be equal to Vp max into Ip max, which is given as 15.4 into 15, which will come out to be 231 watts. And from the data sheet, QC max for TH equal to 27 degrees Celsius is 130 watts. Therefore, coefficient of performance will come out to be 130 by 231, which is 0.563. Which of the following statements is true? As the temperature difference between hot and cold sides of Peltier cooler increases, voltage across the cooler, it will increase, it will not decrease. So therefore this is wrong. As the temperature difference hot and cold sides of the Peltier cooler increases, removal of heat from the cold side decreases under the given condition of constant current. This is right. Because as the temperature difference between hot and cold side of the Peltier cooler, as we are increasing the delta T, then removal of heat from the cold side will decrease for constant current, right? Next is coefficient of performance can never be greater than, so we have already solved numerical problems where it was coming out to be greater than 1, and you can see that there are that this will happen for a very efficient system, and we want the system to be greater than 1. We want the coefficient of performance to be higher, otherwise Peltier won't be a feasible solution. The current through the Peltier cooler is allowed to exceed the rated current. No, we won't do that, because if the current exceeds the rated current, then as we have discussed, that the I square R losses will increase, and because of these increase in these losses, our QC, the pumping capability will reduce, which we don't want. Okay, so we won't operate the Peltier module at higher than the rated current rating. Okay. An aluminium heat sink in the figure shown below has a temperature of 50 degrees Celsius on the higher area surface. Let us say here temperature is 50 degrees Celsius, and on the other side it's 50.1 degrees Celsius. What is the power dissipation of the heat sink in watts? So they have asked us to calculate the power dissipation of the heat sink, whose dimensions is given as 40 cross 40 cross 3.5 in mm, and they have also given the value of K, that is 211 watt per degree Kelvin per meter. Okay, so we know that this is a convection problem. So in this, Q is given by K delta T by delta X. We already know Q, we already know A, that is orthogonal area, that is 40 cross 40. So I am converting this into meter square, and delta T is 0.1 degrees Celsius, and delta X is this, that is 3.5 mm. This will give out the Q to be 9.65 watts. For the data given in question 5, what is the thermal resistance of the heat sink? Now, we know that when we compare these two equations, Q is equals to Ka delta T by delta X and Q is equals to delta T by R theta, then we know that our thermal resistance R theta is equals to delta X by Ka, right? And we know all these parameters. Delta X was 3.5 mm, converting it into meters. K was 211 and area is 14 to 10 to the power minus 6, converting it into meter again because K is also given in terms of meter. So this will come out to be 0.01036 degrees Celsius per watt. Next is problem number 7. An aluminum heat sink is used for
Excuse me,
forced.
ma'am.
Yes.
Question number 6 answer is correct, but in the answer it was given wrong. I got the same answer, but got the 0 marks in this question.
Yes, they have mentioned it as 10, so they
10,
will.
10, they have mentioned 10 between 9 to
Yes, yes,
11. Then
yes, yes,
oh,
yes. That was a mistake. They will correct it in the
okay, okay,
solution.
okay, okay. Thank you.
Okay, okay. So next is an aluminum heat sink is used for forced convection cooling, as shown in the figure below. What is the Reynolds number for forced convection cooling? If velocity, they were asked us to find the Reynolds number. They have given the velocity of air u as 10 meter per second, and kinematic viscosity, that is nu, is given as 1.8 into 10 to the power minus 5 meter square per second. So we know that for this direction of flow, characteristic dimension for this direction, characteristic dimension will be 40 mm. So Reynolds number R is equals to ux by mu. So u is 10 meter per second into x is 40 into 10 to the power minus 3 by mu is 1.8 into 10 to the power minus 5. So R will come out to be 22.222 into 10 to the power 3. So next question is, uh, so in the heat sink discussed in question 7 has been used for forced convection cooling. So now we are doing forced convection cooling and calculate the power dissipation in air. So in air, how much power is dissipated? If the temperature of the heat sink is 70 degrees Celsius and the ambient temperature of the surrounding air is 30 degrees Celsius. Consider the expression for Nusselt's number. So they have given standard equation for laminar flow and for turbulent flow. So we know that in the previous question we have calculated R as 22.222 into 10 to the power 3. So we know that we have to use these formulas. The one for the laminar flow. This is the formula that we'll use, okay? Because R is less than 50,000. Sorry, it's not 50. So N will be 0.664 into R ki power 0.5 into V by delta ki power 0.33. And the kinematic viscosity nu is given as 1.8 into 10 to the power minus 5 meter square per second. And delta is the thermal diffusivity, which is given as 2.6 into 10 to the power minus 5 meter square per second. And the Reynolds number we already know, and the dimensions of the heat sink are 40 cross 40 cross 3.5. And thermal conductivity is 6 watt per degree per meter. Okay. So now, in order to calculate the power dissipation from all sides of the heat sink, if you look at this heat sink, there are two sides, right? One is the top side and another one is the bottom side. So if you just draw the diagram of the heat sink, then because of the forced flow, this is the direction in which heat is flown. This is 40 mm. This is also 40 mm. And this height is 3.5 mm. Now, first we need to calculate Nusselt number. We all know that, right? Because power dissipation formula Q is equals to Ka n Nusselt number delta T by X. So we'll have two sides of this block. We'll have the side from which the heat will be dissipating and then the top. So for the side, if you look, the Nusselt number equal to 0.37 into Reynolds number's power 0.5 into nu by delta the power 0.33. Now we know all these values. From that you can obtain the Nusselt number as 87.67. Now we know that all these parameters will remain for both side and top. So therefore Nusselt number side will be same as Nusselt number top. Okay. Now when you look at the other parameters that you need to calculate here is so delta T. So delta T
Madam,
is yes.
can I ask the question?
Yeah,
In
sure.
earlier problem number 3, that we have the same dimension of the heat sink. That okay. Of
Uh,
problem 5,
yes.
we have the same dimension of the heat sink,
Yes.
and there we use the formula Q is equal to Ka delta T by delta X. The here it is the forced cooling, so the Nusselt number is coming, and
Yes.
there it wouldn't come there. In
Yes.
in fact, that is the only difference. If it is forced cooling, it is number n will be coming here.
Yes, yes, yes. Here
And
forced convection here,
uh,
there forced convection is happening.
and a forced convection, if it is through fluid, also it will be different. That n will change.
Yes, and will change depending on what kind of fluid it is and whether we are using. And if we are using fan, uh,
Fan.
then it will be the speed of fan will also come into picture.
Okay. The number n will change according to
Yes,
that.
yes.
Okay. Okay. Thank you.
Okay. So here, yeah. So delta T is 70. That is heat sink it as 70 and ambient is 30. So delta T we have is 40 degrees Celsius and the characteristic dimension. Now depending on this again, heat flow direction. Depending on this heat flow direction, X is 40 mm, right?
Ma'am,
Yes.
we will consider other one no 0.664 expression na, in place of 0.37 because national the Renan number is 222 22 into 10 power 3 na.
Yes, yes, yes. Sorry, sorry. Yes, I have written here the same.
We should use
Okay.
other one.
Yeah, yeah. Sorry. So it will come out to be the same only. I wrote the wrong formula. Yeah. So the characteristic dimension will be 40 mm and so the only parameter that will be differing will be the areas. So when we are talking about a side, so the side is having this is the side, okay? So this is having dimension 40 cross 3.5 into 10 to the power minus 6, and when we are talking about the top, it is having dimension of 40 cross 40. So this is the only difference that is happening between the Q side and the Q top. So therefore, we can calculate them simultaneously. Q is equals to Q side plus Q top, right? And from Q side, these are all the common parameters, so we can take them out. Now this thing we have to take care here. We have to multiply this by 4 because there are 4 sides, right? The rest will remain the same. Initially we had taken cylinder. So there we didn't have to multiply, but here will have to multiply this and it will come out to be so it will come out to be 4.923 watts. So you can check the calculation again. I hope I haven't made any mistake. But this is the way you will have to solve this. Okay. And the next questions were fairly simple. You have already seen the values of thermal conductivity of these parameters. So initially they had asked the lowest, that is air, and the highest we know that it's the copper. Okay. So if you have any other doubts, please feel free to ask.
Then
Otherwise,
question number 8. Uh, Answer is not in the option.
question number 8.
8, yeah. That
Okay, yes, in this question also they had done a mistake. Actually, they had given the answer by considering only one of the sides.
so yeah, that's why there no options is not there.
Okay. Okay,
What
so
what they will do?
they will mostly award marks to all. Mostly they should do that. I hope so they do that.
Madam,
Yes,
so we have to consider all the sides of the heat sink,
yes,
four sides plus top side.
yes,
If we will not see these A sides, all four sides, then the answer is will be 3.96.
yes. That is what I'm saying. That while
But
doing the
if you
calculations,
calculation,
they
if
have
we
done
take
that error. So
A side, that it will come 4.9.
yes, yes, yes. That is a mistake they had made. That is why they had got the wrong answer.
But which is the correct approach? That we have to take all the sides as well as top side.
Yes, yes, definitely. Because practically, if you think that it won't just dissipate from one side, right? It will dissipate from all the 4 sides. It's a aluminium block.
But at bottom side, we have not to consider only that
Yes,
surrounding
yes.
side as well as top side.
That is why we haven't multiplied the top by 2. We have
Hmm.
just multiplied the sides by 4, and there will be 5 sides, right? The sides, 4 sides at the sides, and then one at the top. That's it.
Hmm, hmm, hmm. Okay.
Okay.
And same thing happens if the heatsink geometry, if we have used the anodized heatsink with the perforations, it will increase the A, isn't it? It
Yes.
increases A, and that is why it becomes effective, isn't it? The like is like
Yes.
it
The
is like
area of cross section increases, right?
area of surface area increases of the
Yes.
heatsink,
Yes.
and then it will have theta will be less.
Yes. It will dissipate heat at a very proper rate because area surface area is increased.
Surface area is increasing.
Yes.
Okay.
Okay, guys. Then we'll end today's session.
Okay.